In this video, we will discuss area problem. So this problem leads to the definition of integral. So integral is motivated by area problem, which is one of the problems you can use integration to solve. Okay, before we do that, let's introduce a sum notation, right? Which is sigma notation. So let's see that. What's that? Because we use this notation a lot in the definition of integrals and also during the process of solving the area problem. Sum notation. So in some problems, right, you want to calculate what is the sum of 1 plus 2 plus all the way to plus n here, right? So basically, you can write this as summation I here is changing from 1 to n, right? And I. So if when I is 1, you get 1, you plus I equal to 2, I equal to 3 plus that, right? So this is basically the sum notation. So in general, if you have f I here is a function of I, right? For I here being a natural number, natural number. The meaning of summation I from 1 to n f I. So this will be f of 1 plus f of 2 plus all the way to f of n. Depends on what is n. N might be 10, 100, or any number you're interested, right? And a concrete example, let's say that a summation I from 1 to 10, let's say I square. So this will be 1 square plus 2 square plus 3 square plus all the way to 10 square. So this upper bound is where you stop. Lower bound is where you start from, right? Okay. So that's the sigma notation, right? Sum notation. And let's see a few examples. Sometimes I want to simplify our sum notation, right? And first fact, a few properties. Property. First one here. If your function is a constant, summation 1, right? I from 1 to n here, 1, right? This is basically 1 plus 1 plus all the way to plus 1. How many ones are there? There are n many. So this is basically n here, right? So in the process of integral, we have to simplify a sigma notation, a sum notation to a function of n, right? We have to do that to evaluate the limit. So this is something which we need to know. Second, in general, if you have summation I from 1 to n here, C general constant, so C is always a constant in our discussion. So this is C plus all the way to C. So this is n times C, right? N many C's, and take a sum. 3, in general, if you have summation I to n here, C times f of I, then this is basically C is a common factor, right? C times f of 1 plus all the way to C times f of n. So this is C times summation I from 1 to n f of I. So you can take the common factor out. A few identities we should know. Okay, one more property here is number 4 here. If you have summation I from 1 to n here, you have two functions, f of I and plus plus g of I, right? So you can regroup it, right? So this is basically f of 1 plus g of 1, then plus all the way to f of n plus g of n. You can put all the f function together, all the g function together, you get two sum notations. So this is same as summation I from 1 to n here, f of I plus summation I from 1 to n here, g of I. So that's basically how do we handle the summation of sums, right? Summation of sum is same as sum of summations. And two more facts we may use. And the first one is summation I from 1 to n here, I. We can simplify this to using some property, right? So this is same as n times n plus 1 over 2. And number 6, if you have summation I from 1 to n here, I square. So this will be same as n times n plus 1 times 2n plus 1 over 6. So we can write this like a many term summation as a single function of n. As n getting bigger and bigger, you can evaluate the summation in a single formula, right? So that's very important. So as an example, right, we can apply all our property above. If you want to evaluate summation I from 1 to n here, 2i plus 1. Now what's this, right? By our property 4, so this is summation I from 1 to n, 2 times I plus summation I from 1 to n, 1 here. And the second term is just n. This first term, apply our property 3, 2 times summation I from 1 to n here, I plus n. So this is 2 times n plus 1 over 2, then plus n, right? So this is a good way to get a new representation of such a big summation, right? Okay, now we are ready to discuss the area problem. So let's see the area problem. Now, what's the area problem, right? You fix a function half of x, which is greater or equal to 0 for all x inside a, b, right? Bounded closed interval. So this function is always non-negative, right? Then what? You can sketch it. So let's say this is a here, this is b here. We have a function which is positive, y equal to f of x, right? This function is always non-negative. Now look at the lines, x equal to a, x equal to b, and y equal to 0, which is our x-axis here. So there's 4 lines here and 3 lines together with a curve enclose a region. A region will be enclosed by this curve and this 3 lines, right? So we call that S. So S here is the region bounded, enclosed by y equal to f of x top, y equal to 0 bottom, x equal to a left, x equal to b, right? That's a finite region. So the area problem here is asking for what is the area of S, right? How do we even define such an area, and how do we evaluate it? This is a general problem. For any function non-negative, you have such a question, very natural question. So what we want to do here is try to give a solution, using a general approach, right? Later we will develop our approach to the definition of integral. We will try to do that on a example, right? Let's see our example. We have an example here. We fix our curve to be y equal to x squared. So that's a very easy curve, right? First non-trivial curve. If you have straight line, you get triangles, then you can evaluate the area using the triangle formula or trapezoid. So we have a function y equal to x squared. And also we have two more lines, enough because we have intersection point, and y equal to 0, which is a base, and x equal to 1, right? So you have intersection point here. We get this is 1 here. This is our right bound. Right, this is x equal to 1, y equal to 0. You have intersection here. So let S be the region bounded by these three curves, right? And we want to calculate the area of S, right? We want to find the area of S, right? S is this blue shaded region. So this is our S here. We want to get the area of S. And for sure, this is not a trapezoid or rectangle or anything, right? So we want to develop our understanding of area to such a irregular region, right? Let's try to do that. Let me try to sketch a few pictures, right? So let's try to sketch a few pictures to illustrate the process. So clearly we don't have any ready-to-use formula, right? Anything ready to use, we don't have that, right? If you don't have any ready-to-use formula, one thing you can do is try to approximate it, right? We want to get a good way to approximate the area of the region, and hopefully our approximation getting better and better during the procedure. And we take a limit, you get exact area of this region, right? So that's basically the idea we have. So this is our parabola. This is our parabola. This is our parabola. So this is y equal to x squared, y equal to x squared, y equal to x squared. We have our right line here, which is 1 here, 1 here, and 1 here. So this under y equal to x squared, above x-axis, on the left side of x equal to 1, the region, the area of the region we are looking for, right? Now, how do we do that? Okay. So the idea here is for approximation, right? But we do know how to calculate the area rectangle. Let's try to fill in rectangles, right? So first we divide our region into two parts. So this is 1/2 here, right? And then you get using the left endpoints, you get rectangles. On the right side, we get this rectangle. On left side, you get this rectangle, which area is 0, right? Which is just a line segment. Using the right endpoint, you can get another set of approximations. So this area of this and the area of this, right? Let's try to calculate L2, the area obtained through the rectangles formed on the left endpoints, right? So because from left endpoints, get function value, scatter line segment, you get a height. And so left side, that's kind of, hopefully that's not hard to evaluate. This is what? So we know that the length, the width of each stripe is 1/2. So 1/2 times height for the first half, height is 0, 0 square, plus 1/2, the height is 1/2 square, right? Now let's try to calculate the area of the sum of the area of the right triangles, which means the right rectangles, right? Which means the rectangles obtained through the right endpoints of the interval, right? So R2 is basically 1/2 times 1/2 square plus 1/2 times 2/2 square, right? And so now you can see that the area of S, this S is between them, right? We know that this two red rectangles lies under the region inside the region of S. This two rectangles obtained through the right endpoints. So this is contains S as a region inside, right? So this is true. You get approximation clearly by looking at the picture. This is very bad approximation. The error is huge, right? And because the first number here is 1/8, second number here is 5/8, right? Their difference is 1/2. This is not even very nice approximation, right? So how do we make our approximation better and better, right? Think about that. This error is very big because your stripe is very wide, right? If your stripe is get narrower and narrower, gets thinner and thinner, then approximation will get better and better, right? So let's try to do it one more time. So if you have divide this into 4 subintervals, right? And so this will be 1/4, 2/4, 3/4, and 4/4, right? In a similar manner, we can form 4 stripes. We can use left endpoints to form 4 rectangles. Also, we can use right endpoint to form another 4 rectangle. The area of the region lies in between them, right? Because the green region contains S as a sub-region, and the S contains the red region as a sub-region, right? So get our L4 in this case is 1/4 because the width of each small stripe is 1/4 times 0 square plus 1/4 times 1/4 square plus 1/4 times 2/4 square plus 1/4 times 3/4 square, right? And you get R4. So this is 1/4 times 1/4 square plus, let me go back to green, and 1/4 times 2/4 square plus 1/4 times 3/4 square plus 1/4 times 4/4 square. So the area of S is in between these two numbers, right? You can evaluate them, right? And the first number is basically what's that? You can do the calculation here, which is 0.21875. This number here is 0.46875, right? You can see that you get a better approximation, right? In the similar manner, you can try to get a better and better approximation. In the next step, you can divide this into 8 stripes, right? So this is 0, 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8 to get thinner stripes. In a similar manner, you can get the rectangle enclosed. I mean the rectangle formed using the right endpoints. Or you can do that using left endpoints. Right? You can calculate AO8. You can write that down. So this is 1/8, 0 square, plus all the way to 1/8 times h/8 square, right? If you want to write down a summation using our standard summation notation we just introduced, so this is summation I from 1 to wait, the last one should be 7, right? This is the left endpoints, so the last one should be 7. So this should be 7. So this is 1 to 8. So this is I minus 1 square over 8. Also, you can calculate R8. This is 1/8 times 1/8 square plus all the way to 1/8 times 8/8 square. So this is summation I from 1 to 8, I square over 8, right? So this is basically how do we get better and better approximations, right? How do we make our approximate better? We just make our division finer and finer, right? Make our index here getting bigger and bigger. So we know that the area for sure of S is in between them, right? So in general, we can define what? Define Rn, right? If n is 2, we'll get R2, R equal to 4, get R4, right? In here is equal to summation I from 1 to n here. If you divide 0 to 1 into n many subintervals, the width of each subinterval is 1 over n, right? Because total length is 1, you divide it into n smaller pieces. So 1 over 8, we are using the 1 over n, sorry, 1 over n, right? We are using the right endpoints. So this is I over n squared. And ln here is summation I from 1 to n here, 1 over n I minus 1, which is left endpoint squared, right? So the area, we are ready to write down the area. So as you can imagine, right, the area of S should be the limit, right? So this is the limit as n go to infinity Rn, right? Or can be as n goes to infinity Ln, right? So this is basically how do we define integration. This is also the integration from 0 to 1 x squared dx. So, but this is how do we develop the idea of approximation into a standard procedure. Eventually, we have such a definition here. And okay.